Who's recording?
That's me.
Oh, okay. Awesome.
All right, we can start. We can admit everybody, but I think we'll trickle in. That's the way things work here. So, on behalf of the U.S. Embassy, I would like to welcome you to this second session of the Ambassador's Waters Expert Program. It is a little early, and we realize that people sometimes show up a few minutes late. So I'll just say we appreciated that there was a lot of people who were at the last session, and my guess is that they'll be trickling in over the next few minutes. Please take this time before the session actually starts to go to the bottom of your screen and look at the icon that looks like a globe of the world. It's called, should say, interpretation, and select the language that you would like to listen in. So you can select Uzbek, you can select Russian, or you can select English, depending on the strength of your understanding. We do realize that, as I said, people will be trickling in. So I'm going to leave it up to our two experts, Neil Dabrowski, representing the U.S. Geological Survey, and Amy Mybeck, representing the U.S. Environmental Protection Agency, on exactly when they would like to start. I would like to also say, before we get started, that this, the U.S. Embassy, which is the Department of State, is appreciative to our sister agency, the Department of Interior, for hosting this session. This is, in other words, a collaboration of 4 U.S. government agencies, and it represents the best that we have in terms of expertise about water quality issues. If there are questions today, we encourage you to put those questions in the chat box of this Zoom if you don't have time or are not comfortable speaking out. We would also like to encourage everyone on the call today to add their email, if they would like, to the chat box and tell us who you represent. Which organization? Are you from the government of Uzbekistan, for example? Which part of the government? Are you from a state committee? Are you from a ministry? It's helpful for us to get a better idea of who we're talking to. And with your email, if you want to get a copy of the recording afterwards, or you'd like to have more information from our experts, we will make sure that that's possible. So without further ado, I'm going to hand over to, who is our first speaker today going to be? Is it going to be Amy again?
Yes.
Okay, so without further ado, I would like to welcome Amy Mybeck. She's from the U.S. Environmental Protection Agency, for her presentation. Thank you so much for your patience.
Thank you, Beth. I'm going to go ahead and share my screen now. Can you see my screen okay?
Looks good.
Okay, perfect. Well, good morning, everyone. I'd like, first of all, to thank you all for attending this second event this morning. I understand it's a very early morning for you, so I appreciate your presence. I'm here today to present on water reuse and discuss the challenges, opportunities, and solutions it presents, particularly related to agriculture. So let's go ahead and get started. And please feel free to stop me with any questions you have along the way. Water reuse can provide alternatives to existing water supplies and be used to enhance water security, sustainability, and resilience. In this presentation, I will be discussing planned water reuse rather than unplanned water reuse, which is more naturally occurring reuse applications. Planned water reuse means water systems designed with the goal of beneficially reusing a recycled water supply, often optimizing the overall water use by reusing water to the maximum extent practical within the community or surrounding area, such as agricultural farmland, before the water is reintroduced to the environment by discharge or injection. So some background on water recycling or water reuse. Sometimes I use the terms interchangeably. Sources of water for potential reuse can include municipal wastewater or sewage, rainwater, or agricultural runoff and return flows. These sources of water can be treated to meet fit for purpose specifications for a particular next use. Fit for purpose specifications are the treatment requirements to bring that water from a particular source to the quality needed to ensure public health, environmental protection, or specific user needs. So that was just a little background on what water recycling is, in particular planned water recycling. Next, I'm going to talk about some opportunities. In the Western United States, agriculture is the single biggest user of water. And this is the area in our country where water is the scarcest. This may sound very similar to Uzbekistan. We are using more and more municipal treated wastewater for irrigation of crops. Typically, the level of treatment or fit for purpose specifications for agriculture is secondary treatment, where the wastewater treatment plant removes the soluble organic matter. The benefits of using treated municipal wastewater or sewage is it's a very nutrient-rich source of water that may not have to be denitrified, depending on the use. Additionally, you can also use the solid waste materials or matter, often called biosolids in the United States, from the wastewater treatment process as a fertilizer, therefore reducing your cost of using synthetic fertilizers. Sorry, I forgot to go forward on the slide. I apologize for that. Okay. In the United States, agriculture accounts for half of our nation's water consumption. At any one time in the United States, there will be a drought occurring somewhere. And this is anticipated to only increase with climate change. Some of the benefits to wastewater reuse is that it's a secure, stable supply for agriculture. It can be provided to farmers for low or no cost, and it also provides the wastewater treatment plants with a known disposal method. So next, I will discuss some case studies that demonstrate how water reuse has been used to support agriculture in our dry Western United States. This case study is very simplistic and is in very rural Idaho. Rupert, Idaho is a very small town. Only 6,000 people reside there, and it is surrounded by farmland. The town upgraded its existing wastewater treatment plant to send treated wastewater to nearby farms. It transformed this waste product, wastewater sewage, to a nutrient-rich irrigation water supply and fertilizer for the nearby surrounding farmlands. When the wastewater treatment plant is centrally located near or around farmland, it can reduce the infrastructure, pipes, pumps, etc., and therefore the costs needed to deliver the wastewater to the farmland for irrigation. Next, I'll discuss the treatment categories for water reuse, particularly for agricultural reuse. This is just one approach recently adopted by a Western state in the United States. Under this approach, the various classes of treatment are defined by their respective treatment requirements and applicable performance standards. Simply meaning the treatment requirements and performance standards are based upon which category of either food or non-food crops are irrigated using the recycled water. Crops that are non-edible or non-food crops for human consumption have a lower treatment requirement than, say, commercial food crops or non-commercial food crops. Using this methodology, you can set higher treatment requirements and higher performance standards, such as those shown here on this slide for bacteria, for uses that have a higher risk, such as crops grown for human consumption, and lower treatment standards and lower performance standards for crops with a lower risk, such as non-food crops. This is just one example of the fit for purpose specifications I discussed at the beginning of this presentation. Next, I'll discuss some of the other water reuse opportunities from municipal wastewater. Treated wastewater from municipal wastewater treatment plants is commonly also used for enhanced aquifer recharge in regions with limited water resources. Treated municipal wastewater has the advantage of being relatively consistent in volumes throughout the year in locations where there is a robust wastewater supply in relative proportion to water demand. The consistent availability of treated municipal wastewater is especially important in communities or areas looking to build resilience to climate change, since they can ensure that part of their water supply portfolio will be available even in times of drought. However, water quality considerations for municipal wastewater must be resolved as sufficient treatment is needed prior to reuse or recharge. We don't want or advocate untreated or improperly treated wastewater to be used in water reuse applications. Next, I'll discuss two case studies of wastewater being used to support agricultural irrigation. This example on the slide is a specific example of enhanced aquifer recharge being practiced to support agricultural irrigation. This is a case study located in California, United States. It is in the Central Valley of California, which is a major agricultural region for the United States. and produces a vast percentage of the fruits, vegetables, and nuts for our country. In this part of the country, the Arvin Edison Water Storage District has been practicing enhanced aquifer recharge to support irrigation, agricultural irrigation, since the 1960s. During very wet years, excess surface water is infiltrated through spreading ponds that can be withdrawn later during dry years. This is a very simple form of aquifer recharge. Before this aquifer recharge was introduced, the overdraft was over 100,000 acre feet per year and threatened the long-term sustainability of agriculture in this region. However, between 1966 and 1999, 4.2 million acre feet of water was stored in the aquifer for dry years. This is an example of how wastewater can be used indirectly to support agriculture through aquifer recharge. Another case study that I'm going to discuss also takes place in California. In the Orange County Water District's groundwater replenishment system. This is a very large wastewater treatment plant that recharges the Orange County groundwater basin through aquifer recharge. The treatment plant uses about approximately 65% of their treated wastewater to recharge the aquifer through infiltration basins. The remaining 35% is used to protect the aquifer from saltwater intrusion. As stated earlier, using municipal wastewater is becoming an increasing common practice due to its consistent availability. By using recycled water, this region has become less reliant on imported sources of water while protecting their existing groundwater supplies. Lastly, I want to mention some of the challenges related to using municipal wastewater for reuse purposes. First, you really need to find out what is the planned water reuse. Is it agriculture, aquifer recharge, or potentially potable reuse? And then what is the corresponding fit for purpose specifications needed for that reuse? Municipal wastewater has contaminants in it, besides the bacteria shown on the slide and heavy metals. Pollutants such as pharmaceuticals, hormones, and personal care products like shampoo, soaps, deodorants are present in municipal wastewater. Generally, the fate and transport of these types of trace organic chemicals is quite low and may not be as large of a concern if the water is used to, say, irrigate non-human, non-edible crops. However, if not treated appropriately, chemicals of emerging concern can be a chronic risk for public health in some water reuse applications. And furthermore, identifying such chemicals in wastewater can be difficult. I will say many chemicals are removed via different mechanisms employed during conventional wastewater treatment. However, some will persist and advanced treatment may be needed for some water reuse applications, especially things like potable reuse. So understanding the risks and trying to mitigate those risks is key in the reuse of municipal wastewater. Thank you so much for your time today, and I look forward to any questions you may have. And with that, I think I will turn it over to my colleague, Neil.
Okay, hopefully I am unmuted now.
You are?
Good, let's share screen. Here we go. Okay. First of all, thank you very much for attending tonight. It's my pleasure to be here, and I'm honored to be able to share the work that I've done in my career with all of you. A little bit about my background. I have a PhD in hydrogeology from the University of Waterloo, Canada. And I spent 34 years, almost my entire career, working for the U.S. Geological Survey studying water quality. I began my work in California, and then for the last 20 years, worked for headquarters studying water quality and directing teams studying water quality for the nation. And today I'm going to talk about the groundwater quality assessments, both from large to small scale, and how these fit together with examples from our work in the United States. And we'll talk about some basic principles. In the prior presentation, I talked about also some basic principles and approaches, and I'll reiterate a little of that tonight. I'll talk about analysis of existing data. And then finally, I'll share examples of the findings that we had from multiple scales, from both studies locally and studies that covered the entire country. So first, back in late 1980s, the US legislature asked the US Geological Survey to answer the question, what is the quality of the United States groundwater resources? And actually it was covering all water resources. And we've been doing that for 3 decades now. So what are the broad goals of a national scale groundwater quality assessment? First, status. The assessment identifies the current water quality impairment, describing spatial patterns of occurrence and concentration. Second, trends. It answers the question, how is the quality of groundwater changing over time? Is it getting better or worse? And third, it increases our understanding of processes. What are the major natural and human factors that influence groundwater quality? And ultimately, with this understanding and the description of the concentrations in space in our aquifers, we can build statistical models and predict the occurrence of a contaminant throughout the nation, and also project it into the future using models. So I want to be clear that what our study addressed were non-point source pollution of groundwater quality. This is not leaky tanks from an industrial facility or an accidental spill. These are diffuse contaminant sources from urban development, from agricultural activity, or even just naturally occurring elements. And an example I used in my previous presentation is nitrogen, which is extensively used in agriculture, but is also present in rainfall from combustion products, and near human habitations and urban areas from sewage and septage. So one thing about a groundwater quality assessment we found, especially at the large scale, is that you need to have consistent water quality information. You want to be consistent in your design, consistent in the approach, and develop a conceptual model of your landscape and hydrogeology when you start. And when you implement it, you have to be very detailed and follow strict protocols everywhere. This includes sample collection, sample processing, laboratory analyses, data quality control, data storage. And finally, we use the same statistical approaches wherever we collect our data. Another aspect that's important is in our work is to be comprehensive. That is, collect as much related information as possible, because it's expensive to travel and obtain the sample and process the sample. So analyze as many constituents as you can when you return it to the laboratory. Additional analysis help you understand where the contaminant of concern came from. And finally, obviously, you can't go back in time and new problems arise. So you may need that data to answer a question you have not anticipated. So this data collection should include all aspects of the landscape at the site, the soils, the hydrogeology, the land use, and potential contaminant sources. So what chemical analyses? I should have had a slide here that showed the table we set up in the field covered with bottles, because we collect a lot of samples. First, on the left, many regulated constituents, including nutrients, trace metals such as arsenic, uranium, and chrome, radiochemical compounds, pesticides. We analyze for more than 200 pesticides and their degradation products, and they're a unique challenge because they change all the time. Also, organic solvents such as TCE and gasoline compounds, toluene, xylene, microbiological contaminants, and then finally emerging contaminants, pharmaceuticals, PFAS, microplastics. And then we also collect chemistry to understand the sample better. We collect geochemical indicators such as the major ions, pH, dissolved oxygen, or other indicators of redox, and environmental tracers, stable isotopes of oxygen, hydrogen, nitrogen, give us an idea of the source of the contaminants and the source of the water. And we analyze for age tracers, sulfur, hexafluoride, carbon-14, and tritium. So we know how long that sample has been in transit. So on to the assessment. When we start an assessment, we usually recognize that other agencies may already have been collecting data. So the first thing we've done is collect, quality assure, and evaluate existing data. So the case study I'll share is for the use of what we call secondary use, because it's already been collected by someone else, of multi-agency data for trends in rivers. I'll show an example of groundwater data when I'm finished with this piece, but I'll start with the data for the rivers because there's a very nice series of slides that show both the benefit and the problem. So my team contacted 488 organizations and aggregated their data. We had 25 million records, which sounds great. But over 14 million had missing or ambiguous information for one or more key metadata elements. By this, I mean whether the sample was filtered or unfiltered, the chemical form, the parameter name, or the units of measurement, for example. The result is that metadata harmonization, that is, getting the metadata equal across all these agencies, which is what had to be done to use the data, could be time-consuming, expensive, and inexact. But for a trends analysis of a decade or more, we need a lot of data. So I'll go through these slides quickly, but I think you'll get the idea. So to examine trends for orthophosphate in rivers, we found we had at least one sample for 107,000 sites across the country, each one represented by a blue dot. But then we looked at the limitations. When we threw away the data that did not have complete metadata, or data that did not have data at least as recent as 2011, we lost 93,000 sites. We still had over 14,000 sites. Still looks good. Now, the trend statistical models require a lot of data, and there are a lot of different rules. And especially in the red font, that data had to be collected where we had stream flow information. Well, only 586 sites had all of this information and could be used. And finally, when we actually ran the statistical models, we found that only 231 sites fit our critical diagnostics. So basically, after starting with 107,000 sites, we had good trends statistics for orthophosphate in only 231 rivers in the nation. So basically, we looked at what the value of that data was. We estimated that the data that was lost due to missing information or a lack of stream flow was worth $12 billion. So data could be preserved for uses beyond the original intent if standardized metadata practices are implemented. So be as thorough as possible documenting your sample collection and analyses to preserve the value of your data for the future. And this is the example for surface water, for groundwater. The reason this became critically useful is there was a city in the United States that changed its source of drinking water, which wound up corroding the pipes and putting very large amounts of lead into the drinking water system. So we were asked to answer the question quickly, where in the country are other drinking water systems susceptible to corrosion? So we had 27,000 wells because we had, again, contacted agencies and collected the data. And the map at the right shows on the top where in the red dots indicate wells that are highly susceptible to corrosion because they are what we call undersaturated with respect to carbonate minerals that will line the pipe and protect it from corrosion. And the bottom map shows other areas in red that are susceptible to a different corrosion, that is galvanic corrosion. So again, this was only possible because we already had cleaned all this data from all these agencies in the nation. So now I'm going to return to our own study design. And I shared this slide a couple of weeks ago, but just to bring everyone up to speed, we collected our data at multiple scales. The map at the right shows a map of the country showing the 25 principal aquifers that we sampled. They make up 90% of the drinking water for the country. But then within each one of these, as in the Central Valley of California circled in red, we also sampled at a smaller scale, what we call our major aquifer studies, that sampled only a portion of that principal aquifer. At the next level, inside that aquifer, we sampled what we call land use studies to look at the different inputs of different chemistries from different land uses. And finally, we sampled within one land use to look at the processes that control the quality of groundwater locally due to a migration of a single chemical, or sometimes more than one. And simply the same information. I did want to note that at the smallest scale, the local scale, we drilled our own wells. We installed monitoring wells. At the land use scale, we used primarily monitoring wells or small wells in private homes, what we call domestic wells. And for the major aquifers, we sampled drinking water wells. This just gives a difficult to see picture of the coverage of the country that we had. At the top, the little green dots are wells in agricultural areas, assessing the water quality below specific crops. And the very small red dots were wells we installed in urban areas to look at the groundwater chemistry below urban land use. The middle one is our major aquifer studies. And the last one is the one I called principal aquifer studies, where we covered the entire aquifers with a uniform grid. And these are, of course, the largest scale. And these, the maps are shown in the proportion to the thickness of the aquifer that we sampled. So the top is very thin. The second one is deeper, and the drinking water wells used for public supply are usually quite a bit deeper, on the order of a couple of 100 meters. And another picture of that, the shallowest well at the right would be characteristic of a monitoring well. Again, very shallow. The second well at intermediate depth would be a household well. And the third well at several hundred feet depth, or a couple of hundred meters, would be a public water supply well. One important thing is to keep the wells from different depths separate when you're analyzing the data. Because groundwater moves slowly, they will reflect groundwater from different sources and different times, and they really need to be kept separate, else the analysis will be very confusing. Okay, so now I'd like to share some examples of non-point source contamination at different scales, and I'll start with the smallest scale. We call these flow path studies, and they're often on the scale of kilometers, a few kilometers or less. This study was in the Western United States, in Oregon, an agricultural area. And there was a stream with high phosphorus concentrations. So we wanted to know where the phosphorus was coming from. So we installed wells under the agricultural fields and then at several places, including directly through the stream bed. The stream bed wells intercepted groundwater just before it enters the stream. And although the agriculture was suspected as the source of the phosphorus, we found that was not true. Instead, there was a deeper layer of sediments that had a lot of organic material, including woody debris and peat. This woody debris and peat was releasing phosphorus, which was being transported to the stream. So the phosphorus in the stream had nothing to do with the phosphorus that was entering the groundwater from the agricultural area. It was really due to the deep flow lines that picked up phosphorus from this buried organic material. Moving back to actually where I live, is the Central Valley of California, semi-arid, surrounded by high mountains with snowpack. This might sound very familiar to you. This flow path study was in the Central Valley, so it's in the plains. And we were trying to understand the movement of a pesticide in this area, specifically called DBCP. And we dated the age of the water at each one of the points using tritium, which allowed us to define the direction of flow and the rate of groundwater flow. These wells were sampled in 1994. The pesticide was banned from use in 1979. And what we found was that the higher concentrations of DBCP, shown in the small numbers, probably difficult to read, were 100 feet or deeper. And in some of the profile, the water at the water table had no pesticide in it. So we could see that the pesticide was persisting, but it was moving downward through the system and cleaner water was entering. Now, the red dots show nitrate concentrations greater than the drinking water limit of 10 milligrams per liter. So although the pesticide was moving down, the young water entering the aquifer had very high nitrate from the use of fertilizer in the cropland. These wells were installed under a very sandy vineyard. So the nitrate and pesticides were moving very rapidly through the system. The next example is to look at the land use studies. And we were directed to study the impact of the most important land use in each region. So going back to the Central Valley of California, this area in the insert with the purple are vineyards, and we installed 30 wells distributed throughout the vineyards. And we also studied two other crops in this area, almond orchards and vegetables. The almonds are in triangles, gold triangles, and the vegetables in green circles. What we found, not surprisingly, was that this graph shows nitrate in milligrams per liter. And the nitrate concentration in the groundwater was different among the three crops. The highest concentrations were found under the almond orchards. The next highest were found under the vegetable cropland, and the lowest were found under the vineyards. The numbers on the left show the rate of nitrogen fertilizer application near those different wells. And the differences in concentration match the differences in fertilizer application rate. So almond orchards had the most nitrate and also have the most fertilizer application. This is not very surprising, but it's also not always the case because chemical controls can remove nitrate from groundwater. Now we'll step up to look at the entire Central Valley of Aquifer, which is one of the 25 principal aquifers that we studied across the nation, and a very important one. This shows the type of grid system that we used to select our wells. And just very briefly, we used a gridded approach. Each one of the grid cells has an equal area. And then we select one well in red from all the available wells. So we have one well in each of those equal area grids. This gives us an unbiased statistical sample of that aquifer. And it's also dense enough so we will always identify a contaminant present in more than 1% of the area. So two very important properties. It's unbiased, and it will identify small targets. Just very briefly, you can see that we covered the entire Central Valley of California with these grids. This is much more detailed than we did for other studies in the nation, but we were cooperating with the state as well as carrying out our own national study. So I'm going to zoom to the small area and show you our results. What we found in the eastern San Joaquin Valley of California is that the most common contaminants were natural compounds, natural elements, what we call geogenics. Even though this is the most intensive agricultural area in the nation. So these may be natural, but their distribution has been changed due to man-made changes in the groundwater flow system, and in some cases, the groundwater chemistry. So a quarter of the wells had high concentrations for arsenic, boron, or vanadium, and another group, about 7%, had high concentrations of uranium or other radioactive constituents. In contrast, only less than 5% of the wells had an organic contaminant, despite the very heavy use of pesticides. Most pesticides do not migrate very easily through soil zones and groundwater. But looking at the bottom diagram on the right, you see that that little gold sliver in the bottom right are fumigants. And most of that gold sliver, which are detections above the drinking water limit, are the same soil fumigant, dibromochloropropane, DBCP, that I showed you on my earlier slide. where we had the very detailed information below one vineyard. So some of these pesticides will persist a long time if they can migrate, while other ones do not. And finally, let's look at all of the principal aquifers in the nation. Again, 25 principal aquifers sampled with this same grid-based approach. 90% of the drinking water used for groundwater used for drinking water. And we found something very similar to what we saw in California, which was natural elements, geogenic elements, uranium and arsenic, were more commonly found above drinking water limits. And we estimated the population that might be exposed to these chemicals. And we found more than 30 million people may be using drinking water that has concentrations of natural geogenic elements at moderate or high concentrations. In contrast, only about 7 million may be exposed to moderate or high concentrations of anthropogenic, that is man-made organic chemicals. Now, because we were very consistent in the data collection, we can break this down and examine the data for any one of the aquifers or any group of the aquifers. Now, just reviewing the findings for the whole country again, to look at the individual compounds, we see at the top, arsenic was present in almost 15% of the wells at moderate or high concentrations. And rather than go through all of them, you can see that at the very far right, the green bar, or the bottom row in the table, the organic compounds were only found about 6% of the time. And importantly, no single organic compound was detected more than 1% of the time. So they're very uncommon. And finally, as I said, we can look at data for any grouping of these aquifers we'd like. Here we've grouped them by geology, starting at the left, Western unconsolidated. These are sand and gravel aquifers. And then moving east to bedrock aquifers, hard rock. And we can see at the left that the Western sands and gravel aquifers, which is a semi-arid part of the country, have by far the highest concentrations of contaminants, with almost 25% of the samples exceeding a drinking water criteria. And my last slide, I wanted to maybe a sneak preview of some of the modeling results I'll share in my next presentation. But these two pictures show that different factors control contamination in streams than in groundwater. The map on the right is a model where we've been able to color the entire country by statistically relating the data in the wells to characteristics of the landscape, including the sources such as fertilizer application and the land use such as different crops and different soil types. The map on the right is for streams and rivers. Again, a model based on landscape characteristics and sources. And what you can see, I should point out, the very middle of both diagrams, on the right, we see a large orange blotch. The red areas have nitrate above the drinking water limit of 10 milligrams per liter. This is the corn belt. And there's very heavy nitrogen fertilizer use on corn. And there's a lot of livestock. And it readily enters the streams. A lot of this area also has heavy soils, and there are shallow subdrains that quickly route soil water to the streams, hence moving nitrate to the streams. The map on the left is very different. It shows nitrate contamination of groundwater scattered across the entire nation. So you can have much smaller sources and much different conditions that will move the nitrate through the groundwater system to a drinking water well. But the only place we see very high concentrations in streams is in the very agricultural corn belt. So, in conclusion, if you collect data with care, comprehensively, and with consistency, you can explain a wide range of problems, both locally and nationwide, that you didn't even consider when you started. For the next presentation, I'll be a little more technical, but I'm very open to suggestions and requests. Right now, I hope to address the interaction between surface water and groundwater, the changes in groundwater concentration over time, how we study trends, the long legacy of groundwater that's already contaminated and its impact, and then modeling to predict and forecast, and particularly the value of master variables such as pH and redox and environmental tracers of age and origin. Thank you very much. I would love to address any questions.
Thank you, Neil. If any of our participants would like to ask a question, they can do so now, or they can also put it in the chat box if they prefer. We can address it either way.
Добрый день, господа. Да, спасибо за очень интересную презентацию. Вот у меня первый вопрос вот, к госпоже, значит, вот, кто первый делал презентацию. Вот вы говорили о восполнении водоносных горизонтов. Вот какие у вас критерии выбора этих водоносных горизонтов? Вы же не любой водоносный горизонт выбираете и его восполняете. Наверное, у вас есть какие-то подходы к выбору тех горизонтов по глубине, по литологическому составу, по наличию каких-то слоев и так далее. Можно услышать ответ на это? Спасибо большое.
Could you repeat that one more time, just so I could hear? I had trouble hearing. One more time. Could you repeat one more time? Can you
Да,
hear me?
в общем-то, ну, да, вот мне говорит, надо представить, значит, Мавлянов Тимур Акинович, представляя узбек гидрогеологию. У меня такой вопрос. Могли бы вы назвать вот несколько таких критерий выбора водоносных горизонтов для восполнения? Вот по каким критериям? По литологическому составу, говорю, по мощности, по глубине, может быть, там, или еще наличию каких-то слоев там. Вот как вот вы выбираете те водоносные горизонты, где можно производить восполнение их там? дождевыми осадками или сточными водами. Это, наверное, отдельно, да? Большое спасибо.
Yeah, so I want to make sure I understand your question correctly. So please tell me if I'm not answering it correctly. So most of my presentation was using treated municipal wastewater for either direct agricultural irrigation or indirect through aquifer recharge. And so really what the criteria are is dependent on what the beneficial use, the crop that you're going to be growing, and determining what level of treatment is needed for that specified use, that crop. And so, or in the case of aquifer recharge, what exactly are you going to be ultimately using that water for, and how are you protecting your groundwater resources? So I'm not sure if I'm answering your question correctly, but one of the key things before determining any water reuse is determining what the application is going to be. That determines the level of treatment necessary. And so I apologize if I'm not answering your question. I want to make sure I do. So please let me know if I'm not getting it correctly. I'm having trouble a little hearing, but hopefully, that provides a little bit of context that for water reuse applications, it's really determining the fit for purpose specifications, determine the treatment requirements and performance standards. That help?
Ну, в принципе, вопрос немножко по-другому звучал. Понятно, что
Okay.
нам
Да,
интересно
да.
просто вот выбор тех водоносных горизонтов. Мы, например, занимаемся восполнением при русловых линз, да, вот какие-то есть у нас каналы, реки, значит, и ищем какие-то благоприятные геологические условия, чтобы можно было там производить восполнение. Но вот, например, в каких-то других условиях, вот нам пока неизвестно, да, вот можно ли производить, или вот как вы это производите, скажем, на глубине там 10 метров, 100 метров, 500 метров. Вот есть ли у вас такие примеры, что вот вы производите восполнение ресурсов в каких-то других условиях? Вот это мы бы хотели услышать. Спасибо.
Oh, Neil, do you want to say something, Neil? Go ahead.
I've been working with an area in the Central Valley of California doing this. And there's already been a lot of groundwater depletion. So there is plenty of room for storage. The large challenge is that much of the landscape is developed. So we need to find areas to do the recharge. We're looking at two different things. One, they're installing wells, dry wells, and directly recharging the groundwater. But we're also spreading high flows. There are very strict regulations controlling the river flows for the protection of fish. But during high flows, they want to divert the groundwater. So to find the areas where they can recharge most rapidly, they've been looking at the geomorphology and looking at the historical and prehistorical position of the major rivers, because where the major rivers were where the coarsest sediments are. And they, first of all, they use drillers' logs, of course. But more recently, and that's, there's been a lot of work done on that, but more recently, They're using airborne electromagnetic geophysics, ground penetrating electromagnetic geophysics, carried under a helicopter, and they are flying large portions of these alluvial fans to see where what we call these old buried paleo channels are, because these paleo channels will have the coarsest sediments, so we can get those floodwaters into the ground very quickly. So it's a combination of coding, digitizing hundreds of thousands, actually, of drillers' logs and geophysical methods. And I'd be happy to share more information on that. It's a very active area of research because we need to recharge these aquifers. California's been very bad at protecting their groundwater, and there's very serious depletion. I hope that helps.
Спасибо. Вот еще один вопрос, можно? Вы упомянули, что сбор, вернее, обработка материалов, собранных у вас вот там 2000, там 20 тысяч, 200 тысяч, да, это процесс дорогостоящий. В каком смысле дорогостоящий? Приобретение информации у других организаций дорогостоящий или обработка этого материала дорогостоящая? Вот могли бы разделить вот этот процесс? Спасибо.
Number two, the procedure is expensive. We found that
Понятно, спасибо.
yeah, data was missing. So you would have a analysis for phosphorus, and one agency would be analyzed as just milligrams per liter phosphorus. Another one would be milligrams per liter phosphates. Another one would be filtered. Another one would be unfiltered. There turned out to be a very large variation across all the agencies. So finding the ones that you could document consistently just took a very long time. Manpower.
Ну, вопрос возник, потому что у нас сейчас с переходом на рыночную экономику неправильно понимают. У нас вот в других организациях, когда мы просим информацию, говорят, надо соответствующие какие-то платить. Вот в чем проблема. Спасибо.
I understand. Yes.
Здравствуйте, дорогие товарищи, участники нашей конференции. Я Исабаев Кадыр, представитель Узбекгидрогеологии. У меня вопрос такой, Нилу. Вот вы представили элементы, по которым вы оцениваете загрязнение. И у вас там существует оценка загрязнения по урану. Это как у вас общепринято или в этих местах есть какие-то урановые орудия?
Oh boy. It's standard. There is a national drinking water limit. I think
Понятно.
WHO
А там есть, нет, да, там уран?
also has that is true. If I encourage you to either contact me directly or look at the first presentation, I showed an example we found in areas like in California and other semi-arid areas with granitic soil, that the irrigation water irrigating these areas that did not have a lot of vegetation was increasing the bicarbonate concentration because the plant roots respiring put in more PCO2. And the higher bicarbonate was leaching the uranium. So the young water under the irrigated fields had high uranium concentrations. In many cases, greater than what was allowed in drinking water. And this is an area with no uranium mines.
Здравствуйте. Еще один вопрос был. Вы сказали, что определяете возраст воды. Вы каким методом или как вы вообще-то определяете возраст воды?
It's really fun. This is a absolutely great tool. It's fairly sophisticated, but unfortunately it's going away a little bit. And I wish I had a board to draw on. There are a number of different ways. Most of them use isotopes or some anthropogenic compound. One of the best known was tritium. Tritium is heavy hydrogen, 3H. It behaves exactly like water in a water molecule. But during the bomb testing in the early 60s, the tritium concentration in the rain in the entire globe went up several orders of magnitude exponentially. The half-life is only 12.5 years. So there was this huge peak in all of the rain on Earth, and then it decayed and we stopped bomb testing and it dropped off. So if you sampled groundwater in the rainwater, so people sampled the rainwater and drew curves for the tritium in the precipitation. When that precipitation recharges, you could identify that by counting the decay of tritium in that water because it's so much higher than natural. The same thing then for chlorofluorocarbons. CFCs, refrigerants, very chemically stable. They're entirely man-made. They did not exist before. They also were volatile and put into the atmosphere. So again, all the rain on Earth had chlorofluorocarbons. It was 0 before we started building refrigerants, and then it went up. So again, people sample the rain and have a curve in the rain. Similarly, you can sample the groundwater and measure the chlorofluorocarbon CFC concentration. The third one was sulfur hexafluoride, SF6. Same thing, it's a man-made compound, it's very stable. So it's a whole sequence of contaminants that you can detect at very low levels and trace once the water is recharged. They're very stable and they're very non-reactive. So they move with the water, especially the tritium, because it's part of the water. So isotopes. IAEA is great at this stuff.
Добрый день, коллеги. Вопрос можно задавать? Я постараюсь задавать вопрос на английском. Mr. Dubrovsky, I am Artekov Kader, Chief Geologist, Central Uzbekistan, filed a hydrogeological expedition under Uzbek hydrogeology. My question is, if I am not mistaken, you are studying aquifers and depletion and the pollution of groundwaters in 4,000 wells. Is it enough? And what area it's for whole United States or California? And in what criteria do you choose for holding wells, drilling wells? Or do you understand me?
I'll repeat. What area were the 4,000 wells in? The answer is the whole country. And your question was, is that enough?
Yeah. For studying whole aquifers.
So I'll take that part of the question first. I can send you a publication where my colleague did the statistics. And if you look at the binomial distribution, you can calculate your confidence in detecting a certain portion of the area that is contaminated. And his calculations show 60 to 90 wells in even a very large area will be adequate to confidently find a target that's larger than 1% of the total area. So it's scale independent. 90 wells in 100 square kilometers, 90 wells in 10,000 square kilometers, because it's a proportion. So I'd be happy to share that with you if someone can send me email information. So yes, the 4,000 wells is adequate. And then since we sampled 25 areas and then put all the data together, we have a very, very high confidence level that we would have found a contaminant present somewhere in the nation. I think the second part was the criteria for choosing each well. Is that correct?
Which criteria do you drilling wells? Choosing drilling wells in depth, or pollution or depletion.
The well locations were random. Again, we actually were trying to stay away from known sources because we're looking at non-point source pollution. Industrial accidents, spills, there are regulations that cover that. So we were not looking at that. So the well selection is random. We only drilled monitoring wells because it's too expensive to drill deep wells. So we drilled monitoring wells when we were working in streams or just under agricultural areas to cover 1 kilometer or 2 and maybe 200 feet. Other than that, we used public wells. It's very expensive to drill, you know.
Thank you.
Здравствуйте, уважаемые участники мероприятия. У меня есть вопрос, можно? Я являюсь начальником Государственной службы геологического мониторинга при Узбекгидрогеологии. У меня 2 вопроса. Первое. Как мы знаем по практике, что в тех регионах, где дефицит поверхностных источников воды, обычно используют подземную воду. И тем не менее они используются интенсивно, что приводит к истощению их ресурсов и запасов. как здесь быть восполнением их запасов? То есть за счет каких источников воды предусматривается либо осуществляется вот пополнение подземных водоносных горизонтов? Это первый вопрос. Второй вопрос. Как вы считаете, что насколько необходимо утверждение ресурсов и эксплуатационных запасов для их целевого использования? То есть в каких регионах считается необходимым исследование и утверждение эксплуатационных запасов подземных вод для их целевого использования? Спасибо.
Neil, do you want to take the
I'll take-
second question, or how would you like to handle that?
Go ahead, Amy. Take the first, please.
I think if I understood correct, and please stop me if I did not understand your question correctly. I think you asked what sources are being used for aquifer recharge. Is that correct?
Да, в зависимости от количества и качества.
Okay, thank you. Okay, thank you. So typically we see, like I mentioned a lot, municipal wastewater, sewage, treated sewage is a major source of water because it's consistent and reliable. It's never really going to run out. So you always have this wastewater as a source of water to use for aquifer recharge. We also see in certain areas of the country, rainwater be used extensively as well. But rainwater is becoming increasingly difficult as we deal with major droughts throughout most of our western part of our country. And so that has become less of a viable option, probably similar to Uzbekistan. It's just not a reliable source anymore. We don't get rainstorms like we used to. Snow melt is not what it used to be. Our snowpack is not that like it was 100 years ago. So we don't use as much rainwater anymore for aquifer recharge in certain parts of the country. We also use sometimes agricultural runoff and return flows for aquifer recharge as well. So water that's coming off of the crops, water that's running off the fields can be used as well. But typically for the arid, dry part of our country, sewage water, treated municipal wastewater, is a very cheap, reliable, consistent source of water for aquifer recharge. And so that's why I wanted to present it today, because a lot of that water is ultimately taken up for agricultural irrigation. Even though it's first used for aquifer recharge, ultimately it gets used again in agricultural irrigation. Neil, do you have anything else you would like to add to that as far as sources typically seen
Yes.
for aquifer recharge?
I would. First, just to reinforce what Amy said, the city of Sacramento is the capital of California. There is a plan to use the effluent from the region's wastewater plant to recharge, to irrigate agricultural areas, just because there's a deficit and it will help recharge the groundwater basin. The other source that they're looking into here is that, as you know, our climates are prone to extremes. So we will have years with very low snowpack, very low runoff. And then this year in California, we had 300% in the mountains adjacent to the Central Valley, which means we'll have very high flows. As I mentioned, there's a lot of effort to maintain the flows for the health of the fishery. But when the flows are very high, that water should be diverted for recharge. So there's a lot of work going on to understand how to take those very high flows and move them to the appropriate areas for recharge. One problem is there's a very complicated legal framework for who owns water in California. The second problem is the infrastructure is expensive to move that water out of the river, in this case, the American River, to the areas, as I mentioned, the paleo channels, for example. And there's conflicting interests. So a professor at the University of California has done a lot of this work to identify the optimal areas for recharge. Unfortunately, someone wants to build housing on top of that area, which would make it impossible to use it for recharge. So there are technical questions, and then there are policy questions. But basically, everyone's very interested in catching the high flows from even small streams and diverting it to agricultural areas. In fact, there have been demonstrations. Many of the farmers believed that flooding their orchards and vineyards would hurt the crop. But there has been work here, at least for our crops, and I know in vineyards, that the vineyards could be submerged for up to, I think, about 2 weeks without harming the crop at all. So it becomes a very, very useful information to know you could flood that field, recharge. In our area, orchards and vineyards grow on very sandy soils. They would need well-drained soils, perfect places for recharge. So we're trying to develop cooperation with farmers to spread these high flows from the rivers onto the agricultural areas temporarily to recharge areas where there's a deficit in groundwater. Then, of course, that groundwater can be used in the dry years when the river's very low.
Спасибо. Насчет второго вопроса как?
Is there anybody
Could you
who's
repeat
afraid
the
to
second
ask
question,
a question
please?
and wants to put it in the chat box? I just want to encourage people to do that as well. Sorry.
Was it how we choose which aquifers in which regions to study?
Нет, как насчет исследования и утверждения ресурсов и эксплуатационных запасов подземных вод в Соединенных Штатах? И в каких регионах считается это необходимым? Исследование и утверждение эксплуатационных запасов для их целевого использования.
Или оценка запасов, или оценка запасов.
Оценка и утверждение.
Very simply, we're a federal government agency. We were given the task of covering the entire country. Now, rather than try to cover the entire country, we prioritized the aquifers. We used water use information, we used population information, and we used irrigation supply information. So we know by picking 25 out of about 60 or more aquifers that we have most of the population, most of the agricultural use. And again, there are large areas that we did not sample at all, but they are mostly arid, forested, with no population, no public drinking water supply, and very little agriculture. And I must say, there are problems everywhere of different sorts. There are problems with very young water, with recent organic contamination and fertilizer contamination. And we found one deep carbonate bedrock aquifer in the middle of the country where the groundwater that was being used for drinking water was thousands of years old and had unusually high concentrations of radionuclides. So very different geology, very different problems.
Hello, everybody. On behalf of Uzbek Hydrogeology, we would like to express our gratitude for organizing this type of seminar between US and Uzbekistan. And thank you very much for US Embassy and translators. In the future, we will have productive and fruitful meetings like this via Zoom. Thank you very much.
Neil, sorry, I couldn't hear that question. So I don't know if it was for you or for me. I had a hard time hearing.
I heard a very gracious thank you. It was truly our honor to be able to share our work with you and the work we've done here for the US government. Thank you very much for attending, and always very happy for any follow-up questions that you would like to send. Thank you.
Yes, thank you so much for your time and attendance. We greatly appreciate it and look forward to any opportunities to work together. Go ahead, Beth.
We have another question. Sorry, it's hard, there's sometimes a delay. We have another question coming in from Rushona. I don't know if she's going to type it or speak it out loud. I don't know if she has sound. She is one of our colleagues from the CDC here in Uzbekistan. Rushona, if you would like to, go ahead.
Thank you, Beth. Good morning, good evening. Thank you for, first of all, thank you for exciting presentations to our presenters. And I have questions to Dr. Amy Maybeck. So in her presentation, she mentioned using wastewater to produce hormones. And my question is, in which kind of hormones production it's using? And it's known that wastewater contains estrogen, and there's a several kind of research about the implication of wastewater on cancer development. So my question, and I'm curious about the estrogen-free wastewater treatment. Thank you.
Yes, thank you for your question. And I see it also in the chat. I believe it's the same question. So thank you for sharing that question in the chat as well as verbally. So you are correct. Municipal domestic wastewater will typically have high concentrations, potentially, of estrogens. And that is a major issue for the reuse applications of municipal wastewater. Conventional wastewater treatment processes, such as primary and secondary treatment, may not remove these estrogens. They're very complex compounds that conventional wastewater treatment plants were not designed to treat. And so we do see concentrations of estrogen in the final wastewater that is sometimes discharged to rivers and streams, but also reused for irrigation purposes. So it is of continuing research, and we are continuing to see pharmaceuticals such as hormones, and particularly personal care products like shampoos and deodorants that have chemicals in them that are called forever chemicals, and they do not break down very easily at all, and definitely are not treated through conventional wastewater treatment processes. And so when using or considering reuse applications, it's really important to know that the wastewater may contain chemicals like hormones that are not going to be treated with the conventional treatment methods. And therefore, things like direct potable reuse is not always considered appropriate because you can't remove all of those chemicals with conventional wastewater treatment. You would have to do something much more advanced to remove those chemicals, and that's usually very, very costly. So I think we are continuing to discover more and more chemicals are in wastewater. And like I said in my presentation, some of them are very difficult to identify as well. So it is continuing to be ongoing research. And that's why sometimes using wastewater for less risky reuse applications, like non-food crop, non-edible human crops, is considered a better alternative because you have a lower risk potential for these kind of, emerging contaminants to be in there and be humans be exposed, ingest these chemicals through such, food crops, things like that. So maybe things like silviculture, growing trees, growing cotton, things like that might be an alternative to more direct exposure things such as growing fruit or vegetables. So very much a great question. There's still a lot of research, and the more we look at domestic wastewater effluent, treated effluent, the more we find is in there because of the products that we're using and the chemicals and the drugs that we're taking every single day as humans end up in our wastewater and are not always treated using conventional treatment methods.
Thank you.
Mm-hmm.
Can you hear me? I think we have another question in the chat box, Amy, either for you or for Neil. It's from Ivek Kojaev. He's our colleague, also from CDC. I'll just read it out so it can be translated. Is there any studies or any concerns on the antimicrobials in the wastewater from the farms? Is there any screening programs of the AB? I don't know what the AB is, I'm sorry. In the wastewater.
Antibiotics, yeah.
Antimicrobial, okay, thank you. And screening of the water for resistant bacteria. That's a great question, especially in an Uzbek context, because antimicrobial resistance is a big concern in this region.
Yes, so to answer your question, there are studies going on to figure out are the antimicrobial agents in the wastewater from agricultural ag return flows and agricultural irrigation runoff. And so again, that's a major concern, especially when using any agricultural runoff for aquifer recharge. So yes, there are ongoing studies, and I'm not sure if there are screenings right now for that per se, but I think to me, using agricultural runoff or return flows for aquifer recharge poses a lot of challenges because you have a lot of these contaminants that are going possibly to be present and may not be adequately treated before used in, say, an aquifer recharge application. So great question. I think it's extremely on point both for the US and Uzbekistan. I don't know, Neil, do you have anything you would like to add to that as well?
I do not, thank you.
Okay.
questions, we still have time. We're still going for another 20 minutes. If there are questions, I want to encourage people to step forward. You have two really strong experts here. If you are not comfortable speaking out loud, you can type it in the chat box. We also would encourage you to put your email in the chat box so that we can make sure you receive these presentations today, and the recording if you would like as well. Okay, please step forward if you're interested to ask a question.
I'd like to answer a question that was asked 2 weeks ago that I failed to answer correctly. The question that I misunderstood, the question that I answered was if we see transport of contaminants from the mountains to the lowlands, to the plains below. And I addressed that for California, where we had gold mining in the mountains. But reviewing the notes, the question was, do we have, and also looking at the literature on the legacy uranium mines, I understand your uranium mines are in the highlands. And we don't have uranium mines in the mountains in California of any significance, but we do have them in mountainous areas in other parts of the country. And so there has been contamination of rivers with wastewater from uranium mines. But the biggest problems that have occurred were from tailings dam failures. So there have been a couple of events where there were some extreme precipitation events and they breached the tailings dams, and very, very large amounts were flushed down through a large river system, contaminating a very large area. So the stability of tailings dams in these areas in the United States anyway is a serious concern. Oddly enough, a long time ago, I did my PhD dissertation on a uranium mine in Canada. It's a very humid area with a lot of precipitation. It was a Precambrian conglomerate, a very different type of uranium deposit than you have. But the milling of that uranium ore released radium into the surface water system, and it contaminated extensive river networks, and it was being taken up in the food chain, and the indigenous people were being exposed to high radionuclides by eating fish because they did a lot of harvesting of the native fish. When they controlled the releases from the mines, the problem did clean up. It did go away. But there certainly can be potential for migration from the mines.
Neil, I'm sorry to say I don't have any background on this, but my understanding is that the Uzbek government is doing a uranium tailing cleanup right now, and I think it might be close to finishing. It's been in the news. So I don't think it's unique to the United States. I think both countries, there's a lot of uranium here actually, so it's a great topic for Uzbekistan as well. As you said, it's a dry, arid climate, and they have huge reserves as far as I understand it. I mean, radioactive, non-radioactive. Okay, I think there's a question from Ibec. So I'm going to read that out loud so that it can be translated. Just a moment. The water use in California, I hope that's what he meant, is
Central Asia.
complicated.
as well.
Oh, Croatia as well. Okay. With rivers crossing several countries, it might be worthwhile to think about bordering river water health. I know California bordering with Mexico and may use the same rivers and water. And how do you cooperate on this issue? Great question.
It is, oh boy. The United States, in this regard, is currently in a crisis because the Colorado River is over allocated. More people want to use it than there is water in the river, and it's also a source of hydroelectric power. And in the last drought, the reservoir got very, very low. So the Colorado River drains to Mexico, and that is the largest cross-border concern between the US and Mexico. I do not know a lot about the water quality other than it's compromised where it crosses from the US into Mexico. Interestingly, there are also cooperative studies going on between the Mexican government and the US government on groundwater aquifers that cross the boundaries, which is an interesting, relatively new venture the past few years. And it's a little challenging because you have to make databases work together if you want to develop groundwater flow models of the aquifers and understand how water moves across the boundaries. So there is cooperative work going on, but I do not know a lot about rivers crossing the boundary. A large portion of the national boundary is the Rio Grande River. So it is shared, but it doesn't cross.
I could speak a little bit about that as well. So we border both Canada and Mexico, and we do have waters that are transboundary waters that go into Canada and south to Mexico, as Neil mentioned. And the State Department does have international joint committees with these neighboring countries to talk about these transboundary issues. I can speak a lot to Canada's because I deal a lot with the issues regarding selenium and the issue that Canada has with water quality related to some selenium mines. And so we do typically have transboundary issues with our neighbors to the north and south. And typically, and Beth may be able to speak to this more than I can regarding the State Department's cooperation with these neighboring countries, but I know, at least I can speak, we do have interagency or international joint committees that we work on these issues with our neighbors to try and tackle some of these very tough, challenging problems that sometimes can lead to, finger pointing, regarding water quality issues. But that's typically how we've done it. I can speak to that. Again, Canada and Mexico are the only ones I've worked with, but maybe the State Department, I don't know, Beth, if you want to, or Elizabeth would like to provide more context as well on neighboring countries and cooperation regarding water quality issues or water quantity issues as well.
I'm not an expert. Maybe Elizabeth has more to say. I would say that for Uzbekistan, this is, as you've probably seen from some of the information I've shared with you, it's very real here. They are sharing river water with a number of different countries and they're downstream. So working together is an existential issue for Uzbekistan. They have to work together, otherwise they won't get the water. And since this country has such a high factor of irrigation required, because so much of the economy is around agriculture relative to some of their neighbors that have more mountains and more snowpack and less agriculture, cooperation is extremely important. So I think your experience, even if it's a little different, is very helpful to people here. Your ideas. That's very interesting about what you said about the groundwater issue. I hadn't thought about that, about sharing aquifers. I don't know, maybe some of the Uzbeks on the call know if any of the aquifers are across the borders with Uzbekistan. Would be a real hot button issue, I would think. Oh, Elizabeth is posting links for those who are still on the call. That's great. That's really nice. So these are organizations that look at the water between the two countries, or in each case. That's great. Thank you very much.
Yes, just to add to what Amy and Neil already said, as Amy mentioned, the International Joint Commission is our interagency organization that monitors water cooperation between the US and Canada, whereas the International Boundary Waters Commission, I believe, the IBWC, is the one that monitors water cooperation between the United States and Mexico. So there are sort of two separate entities that do similar operations and coordination between the two countries, I believe. And you can find more information about each of those on the websites that I've provided in the chat. Neil?
So I will mention that I've been on the scientific end of some of that, and on the opposite border, I was focusing on Mexico, but on the Canadian side, the map I showed of nitrate contamination in the Corn Belt around the Great Lakes, Canada has similar concerns, and we've had very strong partnerships with Canadian water quality agencies, and USGS and the Canadian partners have built models that include the entire watershed for the Great Lakes, because the downstream lakes, Lake Erie in particular, had terrible, harmful algal blooms, toxic cyanobacteria. So they needed to determine where all the phosphorus and nitrate was entering the lake system. So we had very, very good collaboration and built these very detailed models that had all the agricultural and urban sources of nutrients entering the entire Great Lakes system from both sides of the border. Very, very terrific collaboration.
And I just wanted to make one correction. I think I said selenium mines. It's coal mines in Canada. The selenium is the issue of concern. I apologize. But yes, it's we deal with very difficult challenges with our neighbors to the north and the south that I think are probably very similar to the issues potentially that you're dealing with in Central Asia. So I think that was a really great point question. Thank you.
The difference, of course, is that the northern border is, generally speaking, very water rich, except for the interior plains. But the northeast and northwest are very high precipitation. So different issue.
Yeah, sorry, I meant just we deal with challenging water quality issues with our neighbors. That's what I meant, more to that context. Yeah, just we sometimes deal with that with our friends to the north and south, so to speak.
Yes.
I would just like to say, in the few minutes we have remaining, it would be helpful if people who are on the call have suggestions or questions about topics that are related to these areas that they would like to see addressed in a future presentation. Perhaps a deeper dive into the specifics of one of the case studies, or something that was talked about today but was just not given a really in-depth presentation. If you have ideas, you could either say them out or you could put them in the chat box. And I'll also add my email in case you prefer to email me afterwards, because sometimes I do that. And I'd like to again remind you that if you haven't given us your email, you should do so. It's useful for us. We can then share that information from the presentations with you. We also have them in other languages, which you might prefer to see it in Uzbek or in English. And we can do that if you send us your emails. If you're finished, you're welcome to sign off. We'll keep the window open for another 5 minutes. And otherwise, thank you so much for your time today. We appreciate your attendance, and we will send out the recordings. We realize not everybody was able to arrive exactly at 9 a.m. and we want to make sure that some of you can see the whole presentation. It seems that some of you have a great deal of interest in these topics, and so we'll make that available to you to watch on your computer. Thank you again for your time today, and as I said, we'll just stay open a few more minutes.
Thank you very much. We hope that we will have the third virtual meeting on 14th of June, if I'm not mistaken. Thank you very much for all participants. It was very interesting and informative.
You're welcome.
I also want to thank our interpreters and let them know that I think it's okay to go now. We appreciate your time today, and we'll see you soon for the next one. Bye.
Thank you, interpreters.
Thank you.
Yes, thank you very much.
I think we plan to keep the room open for another 2 minutes.